properties. How do I introduce this topic? I'm going to start by imagining a straight fiber optic cable, and the the velocity of the signal through the cable is going to be some function of the properties of the the index of refraction of the cable. Actually, I think they usually give the index of refraction as n. So the velocity of the signal through the cable is the speed of light divided by n, and n is always a number that is 1 or greater. It's 1 for it's 1 for a vacuum of space. I think I'm going to go with big math, with an event happening over at this end at 0, 0, and then over at this end a little bit later, we'll have this be length L, and the time distance equals Vt, so T equals d over V, which will be L over V. L over C over N will be Ln over C. And the position will be L. So we've got two events, one at 0, 0, one at L, Ln over C, and then we would have a third event if it reflected back at 0 again, 2ln over C, 2ln over C. And so that would be where the signal was returned. Now, since this was less than the speed of light, it is possible in principle to actually stay caught up with that signal as it goes from right to left. So let's do what's called a Galilean transformation of that, and we'll do x prime t prime equals, and it goes 1, 1 minus v 0 times the events. We'll do two events. We'll do our three event. We'll do the three events. What the heck? We'll do 3 events. We've got the 0, 0. We got the L, Ln over C. And we've got the 0 and 2ln over C. And I'm actually going to say that we are doing a Galilean transformation to keep up with the light. And so it'll be C over N here. Okay, so what does that do with the first event? That is at the origin of this transformation. It doesn't do anything to the origin. The next one, L minus Ln over C. Ln over C times minus C over N is actually L minus L. So that is going to be 0. And then T is going to be Ln over C. And then the next one is going to be 0 minus C over N. Basically, the C over N cancels, and we will have minus 2L. Will we have minus 2L over C? No, just minus 2L. And the time will be 2Ln over C. Okay, so what happened? The way to imagine this is that in the first incident, we were, this is the situation, the signal is here, and the tube is there. In the next instant, The signal is there and the tube is there. In the last instant, let's see, the signal is there and the tube is there. So that's what this would look like. The guy would go at a velocity. Basically, in this reference frame, the velocity would be 0 on this side, and it would be, and once it got to that end, then it would go at twice that speed on the way back, or 2c over n, 2c over n on the way back. So that's how fast the signal would return, because you would be combining the speed of the tube, the fiber optic tube, with the speed of the signal. They would combine. Okay, that's the version of things that happens if I make my velocity, this direction, exactly the same as that of the signal. We could do another 3 instances. For instance, start here, and then the signal is, say, over here, and then it bounces back over here. So you could have the signal, or say we were going half the speed of the signal, then we would see this signal go that way at half of a c over n, and then that way at, I don't know, 3/2, like 3/2 the c over n, or something like that. So that would be what would happen if I replaced this with 1 minus c over 2n, 0, 1. So it'd be half the velocity that I used before. And you could do it with a more likely scenario. You've got the tube right here, and then the tube moves a little bit this way while the signal moves to here, and then this tube moves just a little bit more this way while the signal moves back. And that would be, so you would see the signal moving quite quickly across the board. I guess each of these is essentially a space-time diagram, except I've drawn the time upside down because I've had time going this way instead of forward. I mean, instead of up. So I could actually draw the path of the light. Let me use a purple pen. Okay. All right. The path of the light in this first situation, in time, it was first vertical because it was essentially stationary, and then it went this way. In the second scenario, it went to the right, and then it went to the left at, I don't know, 3 times the speed, I think, but it's not well represented in the diagram because I didn't do the time to scale. But in the last one, I go to the right, and then I go to the left just a little bit faster, just fractionally faster in that diagram. So a big key to all of this is that it is all based on this value here, which is a velocity, the velocity that you've decided to go in that direction. Put a minus sign in front of it, and it converts the coordinates of the events in the stationary system to the coordinates in the moving system. So we took those 3 events, the event of the signal leaving the left, the signal of the event arriving on the right, and the signal reflecting back to the left again. and we looked at it as a function of how fast you were going relative to the fiber optic cable. So that n over c that I was describing is just kind of an effect velocity. I'm going to replace that with velocity effect. Hold on. So we could kind of think of it as, let's say I started spinning something and it takes a little bit of time for the torsion to take effect going over here to this side. And so that would be the velocity of the effect going through the substance. And we so yeah, I'll just put a wagon wheel over here, and then we'll say that wagon wheel is affected by a torque over here. And what happens is that the effect will go along that, and then it will start to turn the wagon wheel. And when it starts to turn the wagon wheel, that's when the effect of the wagon wheel on the person that's producing the torque will start returning back along there until you get to an equilibrium of some sorts. But I think the time until you get to an equilibrium with the torque here and the angular acceleration here coming to zero, whatever, there's going to be a certain time, and it's going to be it's going to essentially be proportional to 2L over the effect velocity. So it's then what I want to do now is, instead of imagining the Galilean transformation, which we have some control over because we can change our velocity to a desired amount, I'm going to do this other strange transformation, which is 101, and this will be a delta t over delta x. It's it's an inverse velocity. And once again, we'll say x prime, t prime. And I don't know whether we have any control over this thing or not. We'll just say we don't have any control over it at all. It's just this arbitrary value. And it's something that just exists in the universe, this strange phenomenon that makes the time be different at different places. So when we do that, let's call this we'll just call this K, 0, 1. And I don't know whether I need a negative sign in it, since it's essentially an uncontrollable factor anyway. We'll just multiply K by these values. Actually, I'll just write it here. Okay, there's a K. And I'll erase that. And we get 0, 0 as our first thing, as we did before. L and KL over V sub B for our second one, and 0 plus 0 is 0, and 0 plus 2L over V sub E, 2L over V sub E for our last one. Okay, so that equals, or this multiplication equals this, and what happens if you're over here at this end, you directly observe this event and this event, but you don't observe this event. If you're over here, you're going to just observe this event, but you're not going to observe this event or this event. And so what ends up happening is this K is completely is hidden from you. You can't find out what it is. So what was the difference between the Galilean transformation and this transformation? Well, I'm going to go through it all again with the effect velocity put in there instead of all that c over n business. And what I find is that this is the big difference, is that at the end, when you do the Galilean transformation, it actually affects this coordinate here. So these two things are at different places, whereas this one, the one that the non-Galilean transformation, does not affect the x-coordinate at all. So it ends up essentially looking identical to what you had up here. So thinking about it in terms of the bigger picture, in our understanding of space and time, time passes, space doesn't. So as time passes, this transformation does nothing to us, does nothing to our position, does nothing to the coordinates of positions at 0, or the events that happen at 0. But this one, when time passes, it does have an effect on the events that happen at 0. And it actually moves the coordinates of events that would have happened at 0. It does turn out, after putting things in the correct scale, that this parameter and this parameter are actually exactly the same, and they're both based on velocity. The actual equation for this ends up being this, that instead of having our negative v up there, we put negative sinh phi, and instead of putting 1 there, we put cosh phi, and instead of putting 0 here, we multiply this by c and put a negative sinh phi there. And so anyway, it turns out that this is the correct equation that keeps the speed of light constant. So it turns out neither to be the Galilean transformation that goes left and right, or the wacky position preserving thing that goes up and down, but it turns out to be this other thing that goes in and out along the direction of the speed of light. So it's very much like this in that it goes this way and this way, and it is somewhat like this in that it goes this way and this way, except both of those are parameters that are based on the velocity of they're controllable parameters that are based on the velocity of the observer, arctangent of the velocity of the observer.